10.2, Calculus with Parametric Curves. In this section, we're going to learn how to solve problems involving tangents, areas, arc length, and surface area with parametric functions. In a sense, we're going to do all of the calculus we learned so far using parametric curves. Tangents. We also think of tangents when we think of derivatives. Let's read. Suppose f and g are differentiable functions and we want to find the tangent line at a point on the parametric curve x equals f of t, y equals g of t, where y is also differentiable function of x. Then we use definition, dy dx equals dy dt divided by, that's a division sign, dx dt, if dx dt does not equal 0. So just to review this Leibniz notation, this is your derivative of your y function in terms of t, and this right here is your derivative of your x function in terms of t. The top variable tells you your equation name. The bottom variable tells you the variable that you're working with in terms of what variable. So in other words, you can think of it as your y prime divided by your x prime, and t is your working variable. This equation enables us to find the slope dy dx of the tangent to the parametric curve without having to eliminate the parameter t. In addition, if we ever need to calculate the second derivative, we may do so with this equation. D squared y divided by dx squared is the derivative ddx of dy dx. So we have our derivative of dy dx divided by dx dt. Let's do an example. Now this example is pretty lengthy and it pretty much covers all of Calc 1. Everything you learned in your Calculus 1 course is kind of represented here using parametric curves. Let's read this. A curve C is defined by the parametric equations x equals t squared and y equals t cubed minus 3t. A. Show that C has two tangents at the point 3, 0 and their equations. Alright, so to recall, we need to find the equation of these tangent lines. Do you remember how to find an equation of a tangent line? You need to start off by finding the slope, the derivative, right? Start with some y prime or derivative. And your derivative told you the equation of your slope, right? So then you use that to find your slope. So given a point, you're able to, one, find the slope, and second, find the equation of the line using your y minus y2 equals m times x minus x1. So that's what we're going to do. But remember, your order or your direction comes from your t. So to answer A, we need the t. We were not given a t, but we're given the point 3, 0. Notice that 3, 0 is an intercept, right? It's an x-intercept. And so this particular intercept is telling us that when x is equal to 3, y is equal to 0. Thus, using our equations, x equals t squared and y equals t cubed minus 3t, we can find our t. We can use the x. I think the x would be easiest. Since x is equal to t squared, and we're told that x is 3, we're left with t equaling plus or minus the square root of 3. And it also works if we plug in a 0 for y. So we're given RT. So recall from when we learned how to work with parametric curves. We're given RT is square root of 3 and negative square root of 3. And that produces a point 3, 0, since that was the point that was given. And that does work. That checks off. All right. So with that, let's go ahead and find our slope. To find our slope, we need to find our derivative. So our derivative is found by the formula dy dx is equal to dy dt divided by dx dt. So our derivative of our y is 2t squared minus 3. 2t squared minus 3. Our derivative of our x is just 2t. 2t. We have our derivative. We can clean it up a bit by separating that 2 with each numerator term, so that we have 3t squared divided by 2t minus 3 over 2t. We can factor out that 3 over 2, so that we're left with t minus 1 over t. That's our derivative. Now, we're working with this point when t is equal to square root of 3 and negative square root of 3. Now we can use that to find our slope. So we're just going to go ahead and plug in negative square root of 3 and square root of 3 into our new equation for our slope. So that we have our slope would be 3 over 2. I plug in square root of 3 minus 1 over square root of 3. And our other slope will be 3 over 2 negative square root of 3 minus 1 over negative square root of 3. Oddly enough, our two slopes end up being square root of 3 and negative square root of 3 after we clean it up with all the algebra. Just an odd coincidence. It doesn't directly relate to t. It was just a coincidence in this case. So that's our slope. Now second, to find our equation of our tangent line, we need to go ahead and use our slope and our point. So to find the equation of the line, we're going to use our slope of square root of 3 and also negative square root of 3 along with our point 0, 3. So we use our point slope formula. Y minus y1 is equal to x times x minus x1. And I wrote x when I meant to write m. All right, and that gives us two equations. And I wrote my point backwards. I'm sorry. 3, 0, right? Because 3, 0 is what we were given to begin with. 3, 0. In this case, our y is 0. So that makes it easier. So we're just left with y is equal to square root of 3 of x minus 3. And our other equation is negative square root of 3 times x minus 3. So there we have our equations of our tangent line given the point. So What does a tangent line give you? So recall that these are the equations of our tangent line at 3, 0. So they touch our curve of our function. All right, let's go on to question B. All right, for B, let's read our question. Our question reads, find the points on C where the tangent is horizontal or vertical. All right, so tangent lines, horizontal and vertical. Recall your rules of slopes. So we know when your slope M is undefined, you have a vertical line. And when your slope is equal to 0, you have a horizontal line. So how can we relate that to our definition of a derivative? Just so we have it handy, our derivative dy dx is our derivative of our y, so dy dt, divided by our derivative of our x, dx dt. So when can we make it undefined and when can we make it 0? It seems pretty obvious at this point, right? We just set our derivatives equal to 0, but depending what we want. So we can come to conclude that when we have a vertical tangent line, that happens when our dx dt, our denominator, is equal to 0, with the condition that our numerator, dy dt, is not 0. Similarly for horizontal, dy dt, our numerator, is equal to 0, not theta, given that our denominator is not 0. Okay, with that said, we can find our vertical tangents and our horizontal tangents with this at this point, or of our function given, of our function. All right, so we have our partial derivatives. We have for our vertical tangent, I ran out of space, all right. So our vertical tangent, we have when dx dt is equal to 0, our derivative dx dt is 2t. So we set that equal to 0, we get t is equal to 0. Our partial derivative for y, we have 3x squared, or 3t squared. We set that equal to 0, and we get that t is equal to plus or minus 1. Once we solve for t, we get plus or minus 1. All right, so those are our values for our vertical and horizontal tangents. Also remember that the first derivative also gives you your max and minimum. So we're finding our maximum and minimums. Okay, so we're finding our t. Now we need to find a corresponding point for this t. So we have a t of 0, -1, and +1. We need to find a corresponding point for this position in our function, or our curve. We shouldn't say function, our curve. So our equation is x equals t squared, y is equal to t cubed minus 2t, 3t. That was what was given. And we just plug in t. So we get x is equal to 1, y is equal to 2. When t is 0, x is 0, y is 0. When t is 1, x is 1, and 2 is y is negative 2. So we have the points 1, comma 2, 0, comma 0, and 1, comma negative 2. And that answers that question. The question asked, find the points where the tangent is horizontal and vertical. We found such points. Last piece of information, determine whether the curve is concave upward or downward. Recall from your Calc 1 course that this relies on your second derivative. So we're going to have to take the second derivative to find when it's concave up or down. All right. So for C, let's go ahead and take our second derivative. Our second derivative is d squared y divided by dx squared. So we have d divided by, or d dt, our derivative of our y derivative, or our new derivative. So the derivative of our first derivative. So dy dx divided by dx dt. So this is just the derivative of our first derivative. And right here is just our partial derivative from our equation x. So that we have 3 over 2 is a constant, and our first derivative was t plus 1 over t. So we're left with 1 plus 1 over t squared divided by our partial derivative of x, which is 2t. If we clean it up, this gives us 3t squared plus 1 divided by 4t cubed. Alrighty, let's go ahead and find when it's concave up or down. Remember, from here, we set our derivative, our answer, and we find when it's 0 or undefined. So we set the numerator and denominator equal to 0, and we only get that t is equal to 0. So the numerator gives us a complex answer. The denominator, 4t cubed, gives us a t of 0. And so we test on our curve to see when we get a negative or a positive outcome. We end up getting that when t is less than 0, it's concave down. And when t is greater than 0, it's concave up. And that is our part C. Part D is asking us to graph it. Part D of our function is sketch the curve. All right, so we know pieces, we have points. We have points that we found. We have the point 3, 0 that occurs twice. And if it occurs twice, then we give you the hint that's going to happen. That point is going to cross twice. Remember, t gives us a direction, so that means we're going to cross that direction twice. All right. So let's do a quick Cartesian plane. So we have the points 0. Well, from our graph here, we see we have negative the point 1, 2, 0, 0, and 1, negative 2. We also have the point, why did I write a negative there? You have the point 3 comma 0, which was given. We know here we have horizontal tangent lines. So from that, we know that that's a max and a min, right? It's not going to go past that. From our first equation, we got these lines, these tangent lines. So they tell us our curve is going to go along these tangent lines. Right? And I really shouldn't be drawing arrows because we don't know what's going on. Drawing an arrow is such a habit. All right, but we have our t's. So we have our t's, right? So when t is 0, we have the point 0, 0. When t is -1, we have 1, 2. When t is 1, we have 1, -2. So our graph goes with this line. And it just goes from 0 to 1, and it goes this way. But then it tells us also that we cross this point twice. So there must be some other curve going this way as well. So in a sense, we have this graph going this way, which is pretty cool, right? All right, so this is a really rough sketch of what we have using our points given and our calculus knowledge. So our first derivatives that produce maximums and minimums, and our second derivatives which give us a clue as to what's going on with the concavity of the function. All right, if you're overwhelmed, this would be a good point to take a break, come back to the video. Also, you can kind of stop the video from here and carry on out. From here on, we are going over areas and arc length, and we're just going to follow the definition provided, the formula provided, and after that it's just integration. So I think you can continue from there without having to do the remainder of the video. All right, let's continue. Areas. We know that the area under the curve y equals f of x from a to b is a is equal to the integral from b to a of f of x dx, where f of x is greater than 0. If the curve is traced at once by the parametric equations x equals f of t and y equals g of t, where t is between alpha and beta, then we can conclude an area formula by using substitution rule of definite integrals as follows. So we have a is equal to our integral from b to a of y dx. And we said y is our function g of t, so we have g of t. And dx, our partial derivative of x, would be f of t dt. Or, in summary, we have this conclusion. It's our integral from g to t times f prime of t dt. All right, let's do an example. Find the area under the cycloid. Okay, so following our rule above, our definition above, let's go ahead and do this. So remember, your y, it's what's defined as your g of t, and your x is what's defined as your f of t in the notation. So let me put it this way. G of t is your y equals, so you're going to plug in your y equals function. F prime of t is your x, so then you're going to plug in your derivative of x. And that's your equation for our area. So we have a is equal to our integral from 2 pi to 0 of r (1 minus cosine theta), since that is our g of t. And then we need our derivative here. Our derivative derivative in terms, in this case, of theta would be r is our constant, so we have 1 minus, the derivative of sine is cosine theta. So let's plug that in. R 1 minus cosine theta d theta. And something I should have emphasized, we know our limits for our integration are from 0 to 2 pi because that's what we have here, 0 to 2 pi. Okay, let's go ahead and clean this up. Just a quick note. Our variable we're working with is theta, so t is our theta. So r is just a constant. It's just a number. So here we have, let's take r and r out. So we have r squared of 2 pi to 0. And we're left with 1 minus cosine theta times 1 minus cosine theta. So we have 1 minus cosine of theta squared d theta. So we have r squared, 2 pi to 0, 0. Let's expand. So we have 2 minus 2 cosine of theta plus cosine squared of theta d theta. Now from here, we're going to use that power reduction rule we learned back in chapter 7. We can replace that with 1/2, 1 plus cosine of 2 theta. Let's go ahead and make that replacement. So that we have 1 minus 2 cosine of theta plus, since this is a constant, let's write it on the outside. I'm getting ahead of myself. 1 over 1 plus cosine of 2 theta d theta. All right, because each one is its own term, if it's helpful, you can integrate each one separately, right? Let's go ahead and write it that way. We have r squared of, and then we have our integral for 1 minus our integral for cosine of theta plus 1/2, and our integral for 1 plus cosine of 2 theta. All right, and we can integrate each one. So we have r squared times, the integral of 1 is theta, minus 2, our integral of cosine is sine, plus we're left with 1/2 times, now this one's a fun one, right? So we have to use sub, so we have to compensate a 1/2 for that 2 we're going to need for the du. So that ends up being, we have theta plus sine of 2 theta, and that 1/2 we had to use to compensate. And from there, you can go ahead and distribute that 1/4 and combine like terms. So that we have r squared 3 over 2 theta. Once we combined our thetas, we got 3 over 2 minus 2 sine of theta plus 1/4 sine of 2 theta, when our theta is from 2 pi and 0. We plug those in, we're left with r squared is equal to 3 over 2 times 2 pi. 3 pi r squared is our final answer. Let's move on to arc length. If a curve C is defined by the parametric equations x equals f of t and y equals g of t, where alpha is less than or equal to t, less than or equal to beta, where f prime and g prime are continuous from alpha to beta, then C is transverse exactly as t increases from alpha to beta, and the arc length is C is. So our arc length is defined from our limit or integral from beta to alpha of the square root of dx dt squared plus dy dt squared dt. All right. Example 4, if we use our representation of the unit circle given, find the arc length. All right, so our formula is L is equal. Now we're given from 2 pi to 0, 2 pi to 0, the square root of. Now our formula says our partial derivative of x, so our x prime, our partial derivative for y, well, our derivative for y in terms of t, so our y prime. Our x prime would be, the derivative of cosine is negative sine. Our y prime, the derivative of sine is cosine. So let's plug in those derivatives. So we have x first. Sine of t squared plus our derivative for y, we have cosine of t squared in terms of t dt. All right, we can go ahead and expand it, and we get our integral from 2 pi to 0 of the square root of sine squared t plus cosine squared t dt. All right, remember we can write cosine or sine using our Pythagorean identities. So sine squared is the same as 1 minus cosine squared. So we're left with 1 minus cosine squared t plus cosine squared t. Our cosines cancel, and we're left with just the square root of 1, which is just 1. All right, if we integrate 1, our answer is t. So we're left with t, and we're left to plug in when t is equal to 2 pi and t is equal to 0. So our answer is just 2 pi. Example 4. Find the arc length of the cycloid x equals r times 1 minus sine theta, and y equals r times 1 minus cosine theta when theta is between 0 and 2 pi. All right, so we need to find these partial derivatives, right, to find the arc length. Remember your definition for our arc length is our integral from beta to alpha of dx dt squared plus dy dt squared. Let's find these dx and dt's. So start with x. Dx dt is equal to, we have, remember r is just a number, it's a constant. We're working with our t's, or actually in this case it's theta. So this should be theta, because theta is our variable. That gives us r. The derivative of theta is just 1. The derivative of sine is cosine. And then dy d theta would be r. The constant's gone, and we're just left with the derivative of cosine, which is negative sine. So a negative and a negative is a positive sign. So we're left with L is equal to our integral from 2 pi to 0 of the square root of r times 1 minus cosine theta squared plus r sine of theta squared d theta. Alrighty, let's clean up the inside. So we're left with r squared, and now this whole thing is squared. So we have r squared 1 minus cosine theta squared plus r squared sine squared theta d theta, all under a radical. All right, let's go ahead and factor r squared. And it's under a radical, so if we take it out, it's going to be just an r. R is a constant, so we can write it outside of our integral. And we're left with, let's expand this binomial. We have 1 minus 2 cosine of theta plus cosine squared theta, and then we have plus sine squared. You see here that we can replace cosine with 1 minus sine squared. We can make our sines cancel again, like we did before. So we're just left with 1 minus 2 cosine of theta plus 1. So our answer is just 1 plus 1 is 2. So we have 2 times 1 minus cosine of theta. Oh, I keep forgetting to write that square root. D theta. All right, so we're going to use some clever identities here. We're going to use the identity where that power reduction formula. So we had sine squared of x is the same as 1/2 1 minus cosine 2x. So we notice that here we have 1 minus cosine, and we don't have a 2x. So because of that, we're going to write it as a theta over 2 to make up that's being doubled over here. Okay. So if we use that, we can replace it with now let's multiply 2 to both sides. So we have 2 sine squared theta is the same as 1 minus cosine of theta over 2, which is what we have here. So that's going to be times 2 sine squared theta. And usually we don't want the square because that creates a problem when integrating. But once we're under a radical, it's actually pretty helpful. So we're left with 4 sine squared of theta over 2. If we integrate, we're left with just 2 sine theta over 2. Now we integrate if we apply the radical. So once we integrate, we can move this 2 out. We have 2r from 2 pi to 0 of 2 sine, or just sine, of theta over 2 d theta. And we get cosine of theta over 2 once we integrate. And our answer from here would be 8r. As I'm looking at my work, I see that I have a negative 2 here. I think I missed a 2 somewhere, so keep an eye out for that. Next, we have surface area. And again, we have a formula here. Our derivative for x, our derivative for y squared, times 2 pi and our y equation. Example 5, show the surface area of a sphere of a radius of r is 2 pi r squared. All right, so recall from section 10.1, a sphere is parametrized by x equals r cosine of theta and y equals r sine of t. I think we said theta. And if it's a circle, a sphere, our t would be from 0 to pi. All right, let's go ahead and set up our formula. So we have s is equal to our integral, which will go from pi to 0. And we have our 2 pi y, 2 pi, and y is r sine of t, and the square root of, we have our partial derivative of x squared, so we have negative r sine of t squared plus our partial derivative of y squared. Okay, that's it. From there we just integrate, and this one isn't so tricky once we start integrating. All right, we have 2 pi, which are constants, so we can go ahead and move them out. So we have 2 pi from pi to 0 of r sine of t times the square root of r squared sine squared of t plus r squared cosine squared of t dt. All right, just like before, we can let sine squared be 1 minus cosine squared. So our cosines, I'm getting ahead of myself. But that's what we want to do eventually. I'm getting ahead of myself because we first need to get that r out of the way. So let's go ahead and factor out that r squared. All right, we can take the square root of r squared, so we just get r. So we have r times r sine of t, and we have sine squared of t plus cosine squared of t dt. We can let sine squared be 1 minus cosine squared of t. Our cosines add up to be 0, and we're just left with square root of 1, which is 1. And actually, we can move this r squared out too. We'll do that in the next step. The square root of 1 is just 1. All right, we can integrate sine. which is negative cosines. So we have 2 pi r squared of negative cosine of t when t is equal to pi and t is equal to 0. And our answer is just 4 pi r squared. That's it for section 10.2. Your homework is a couple problems, just want to try of each. So 5, 11, 41, and 65. All right, thank you.